I would like to present shortly a new building which is at the moment under construction, and it has been designed according to the cooperation of architectural design studio, Aspectus Architect, and the investor of the building, which I'm going to present, is going to be the investment from the company called Wing. It's not a Chinese company, only the name sounds like that. W is for Wallis. So this investment company actually is one of the largest investment companies in Hungary, and they are developing office, retail, residential, and they have a variety of logistics center portfolio. So the building which I would like to present is actually not official with the final results, so that's why I will concentrate only the preliminary design phase, which is connected to the decision-making process. The outline of the presentation is going to be the following. First of all, I would like to highlight the green building certifications and to talk about a couple of categories in green building certification. Then I would turn to the integrative energy design stage, which incorporates the energy analysis and the building simulation. Then I would continue with our research focus and methodology for the analysis of the building's energy performance, input building operation data, assessing the heating and cooling demand in the function of different carton wall systems, and finally the Hvac system energy consumption modeling by comparing the American ASHRAE Appendix G system with our design system, and finally evaluating the energy performance of the building. So concerning the green building certification, there are three most widespread certifications internationally recognized. First one is from the United States, the LEED Green Building certification from the Green Building Council, which is rating the buildings in different categories according to their performance. The second is the United Kingdom's BREEAM certification, which also rates according to different categories, but it concentrates more on local standards. And finally is the German, the DGNB standard, which already also is a rating system compared to LEED and BREEAM. For this particular building, which you have seen on the first slide, actually we will apply the LEED credit rating system, and our goal is to achieve a LEED Gold certification, which is a pretty high level of certification. The highest level is the LEED Platinum, but the LEED Gold certification actually is the third level from the minimum certified buildings. So actually it needs a higher investment rate. But that rate is going to return later in the lease agreement. So concerning LEED, it has 6 categories, which are sustainable sites, water efficiency, energy and atmosphere, materials and resources, indoor environmental quality, and innovation in operation and regional priority. So actually all categories have mandatory requirements, mandatory prerequisites, which have to be achieved in order for the building to reach the minimum certification level. And today we will talk about the energy and atmosphere category, and only one credit category under this complex is going to be the minimum and optimum energy performance. So concerning the building, it's going to be a 40,000 square meter LEED new construction office building, which is now at the moment registered, and it's under construction. So these are photorealistic renders how the building will look like. At the moment the building is at the 4th level under construction, and it's going to be leased to different companies, different IT companies. If you can see the building next to this one, that building is rented for the Ericsson. The Ericsson company is actually renting the whole building, which is 40,000 square meters, and this new one is going to be the same size and with the same office space property and the same 16,000 square meters of parking, which is underground. Those are actually 4 levels of underground parking. So concerning the integrative energy design stage, in this presentation, we're going to concentrate only on the fifth step, which is called the assessment possibility of energy strategies in the building. And here, the team has analyzed the building envelope attributes, different insulation types, different glazing types, etc., different systems. Then, concerning the lighting levels, the lighting power density, the minimum lighting level, etc. Actually, all the surfaces inside the building concerning walls, floors, and ceilings have their surface reflectance index. So we have also analyzed how will it contribute to natural daylight inside the building. Thermal comfort ranges. The thermal comfort for a LEED Gold certified building has to be minimum category B, which means that the temperature oscillation, operative temperature, etc., all has to be adequately sized. The plug and process loads, well, that actually depends from the company who's going to lease the building, and many companies have different requirements. So actually concerning the plug and process loads, since half of the building will be at the moment leased by a significant company and the other half is under negotiation at the moment, we have modeled the plug and process load to a maximum category. The programmatic and operational parameters have been used according to the ASHRAE standard operation parameters in this first phase. So concerning the research focus, we have to design a building for LEED Gold to be energy efficient and to be environmentally efficient as well. So both are pretty important. So the first thing is to minimize the heating and cooling demands, and in order to minimize the heating and cooling demands, first of all, we have to concentrate on the curtain wall system and to choose adequate glazing types with adequate G-value, solar gains. So we analyzed 3 different manufacturers, and from those manufacturers we analyzed also the costs and also the energy performance on the building from the glazing type with different G-values. So the first G-value was 0.6, the second was 0.5, and the third one was 0.3. And concerning the baseline and proposed HVAC system, since it's LEED certification, we have to compare our building to a standard American building from ASHRAE 19.1, Appendix G. And the building has to be modeled at the same size, but with 40% of window to wall ratio. And for this specific building, the reference HVAC system was the variable air volume, which reheat using also a cooling tower for cooling and a gas boiler for heating. And our system, designed by our mechanical engineers, was the dedicated outdoor air system with fan coil units. So, concerning this system, many improvements have been made, which I'm going to show you now. So, concerning the energy performance analysis, first of all, we had to design the whole building as a thermal model. On the image, you can see the building's thermal model. It was designed in also American software from the Department of Energy, Energy Plus, using a plugin of the software, which is Open Studio for the 3D rendering of the image. So the spaces, since we have a lot of open plan offices, all these open plan offices were actually connected as one air volume, and the fan coil units, which are inside these offices, are actually mapped on the drawings, but this is only a 3D representation. How does it look like? All other are numerical data which can be visualized in geometry. So the first step was modeling the multi-zone thermal model. We had the focus on heating and cooling energy consumption, analyzed active and passive systems, influence of internal heat loss, we determined the heat gains, and we simulated the HVAC systems, and that's how we determined the total energy saving potential. So concerning the input parameters, they are pretty complex because the simulation is actually conducted on an annual basis in 15-minute intervals. So that's a huge amount of data, and a huge amount of data needs a huge amount of input data as well. So the input data was a 30-year average input weather data, which you can see as an example on the left side. You can see, for example, the dry bulb and the wet bulb temperature, and the temperature fall, the temperature curve graph. And below you can see, for example, the solar gain graph also presented in hourly basis. And concerning the thermal zoning, since this is a preliminary analysis, in a preliminary analysis we actually do not need to make all the zones according to the design documents. We can simplify the model, so the model was simplified to 22 thermal zones. Actually, the final construction document has 520 zones, and we simulated the building for 520 zones, but here only 22 zones are displayed because the fit-out plan changed in this 1 year a lot. So concerning the thermal comfort demand and building operation, the heating, the cooling, and the ventilation of fresh air was determined. So first of all, we had to input the parameters according to the owner's project requirements and the design brief, and the design brief has a detailed description what do they require from the building. So operative indoor air temperature has to be 20 degrees, which is minimum during occupied hours, and the maximum operative has to be 26 during summer. So this is all from the description of the design brief. And concerning the mechanical engineering colleagues, they said that the air supply at 22 degrees and air supply at 24 degrees would be the adequate for this solution. And concerning the ventilation and fresh air demand, according to the Hungarian energy efficiency regulations, for 2,500 occupants, which would be in the building, is going to be 120,000 cubic meters per hour. So concerning the operation data of the building concerning occupancy, lighting, and equipment. Concerning lighting, the detailed calculation with smart building technology is only a phase which comes after the preliminary design phase, because then the sensing system and according to the adequate fit out can be determined in detail. So here we have the maximum lighting in the building, and concerning the schedules are taken from the ASHRAE Handbook Fundamentals. How does it have to apply for a baseline office building? And when we conducted the first simulation with different carton wall systems, we have determined that the A1 windows heat addition, which has the least heat gain, which is indicated actually in green, but I see that here the colors are opposite. It has 681, if you can read down there, 681 kilowatt hours of heat addition on an annual basis. Now, for example, if we compare those windows to the windows which have 0.5 and 0.6 G value, then actually the heat addition is almost double of the previous, which means that the heat gain and the window quality we have to invest more in the window quality, because then our energy consumption will be a lot less. And concerning the HVAC system, the baseline HVAC system was, as I mentioned, the VAV system according to Appendix G with cooling tower and gas boiler. And our proposed system was the dedicated outdoor air system with fan coil units. And in order to have better performance and in order to reach LEED Gold certification, we have incorporated air source heat pumps for the air handling units. And the air handling units for the offices are incorporating all these heat pumps, so it means the 4 blocks. And we also have electric water-cooled chillers, and we have dry coolers because they do not use water as the cooling tower, and we can claim credits also for not using a cooling tower on the building, and it's more efficient. And concerning the heat exchanger, we are going to have rotary heat exchangers for the air handling units of 74%, and the ASHRAE baseline is 50%. So that's why we are expecting now better results. And concerning the HVAC system of the ASHRAE, you can see example system here on the left side. That's an example how does an ASHRAE system look like, which was incorporated for the building, but modeled according to the building's needs and sized according to the building's needs. So one more thing, why is this better? This building is better compared to an ASHRAE building. It's because of the thermal properties and because of the very rigorous Hungarian regulations and European regulations for opaque constructions to have thermal properties and glazed construction. So as you can see on the right side, you can see the table where the U values of the walls, windows, green roof, etc. are presented. And down you can see the window to wall ratios. And for example, the carton walls system in U value, for example, the ASHRAE system for the same climate zone has 2.85 U value for the carton wall. Our carton wall has 1.26 because that's adequate to our standards. Our standard is maximum 1.4. Okay, so I'm not going to go through all these thermal properties. The main thing is that actually all the thermal properties, the envelope has to be better. And after performing the simulation of the HVAC system presented the following total values. Concerning the heating has a drastic energy reduction. And concerning the total energy for electricity, using for cooling, pumps, fans, lighting, equipment, heat rejection, etc., the reduction was close to 30%, So actually the heating is one thing which in our case is way better. And in conclusion, today it's really difficult to apply the standards plus compare the building to the same building with the standards which are already rigorous. So actually the investment cost has to be higher at the beginning, and the preliminary design phase actually has to show which way does the investment have to go, because in some cases, for example, if we apply an ordinary system and if we do not operate the system adequately, and we do not have, for example, renewable energy sources, then in the operational period, which has to be claimed after 1 or 2 years, it can turn out that actually the building is performing worse compared to its ASHRAE counterpart. So that's why in the preliminary design phase, we have to make good decisions and also claim these results to the investor, so the investor can decide which is the best investment he can make in order to achieve the certification and in order to maintain the building's operation at a lower level. So according to the glazing types, 47% of additional heat can be reduced, and according to the final simulation, the electricity reduction can be reduced by 29% and the natural gas reduction by 80%. Okay, thank you for your attention.